Every major scientific field, it seems like it needed its own language to really ignite. Physics had to wait for Newton and calculus to really describe motion properly.
Right. You need the right mathematical tools.
Exactly. And electrical engineering. I mean, try doing that without complex numbers. It'd be impossible.
Yeah, absolutely essential for phase and amplitude.
So that brings us to AI. Here's the big question we're diving into today. Has AI found its foundational language? That single unified way to express everything.
The short answer, it's a clear no. Not yet. And honestly, that's a huge bottleneck right now.
A bottleneck how?
Well, we're building AI on these sort of fragmented foundations. It creates friction, makes things harder than they need to be.
Right. Like you've got the deep learning folks mostly in Python, right? Using PyTorch, TensorFlow.
Like the dominant players.
And they're amazing at learning from just mountains of data, scaling things up on GPUs. Fantastic for that.
Absolutely. Unparalleled learning capability.
But they don't really do automated reasoning out of the box or handle explicit knowledge cleanly. If you want logic, you're kind of bolting it on afterwards.
Exactly. It's not native. Yeah. And then you flip the coin. You've got the classic symbolic AI languages.
Yeah.
Thinking LISP, Prolog.
The old school, yeah.
They were brilliant at formal logic deduction.
Yeah.
The rules are crisp, the reasoning is provably sound, but they just completely fell down on scalability. And dealing with noisy real-world data, forget it. And learning from data wasn't really their strong suit.
So we're stuck, basically. You choose learning, which is kind of fuzzy but scales, or you choose reasoning, which is crisp but brittle and doesn't scale well.
That's the dilemma. We lack that single notation, that one mathematical structure that can just naturally express both sides of that coin.
And that lack of unification, it's not just academic, right? It costs time, effort.
Oh, definitely. Time, money, accuracy. It's what stops us from having AI systems that are truly transparent and, importantly, reliable.
Okay, so let's get to the potential solution. We're looking at some really interesting new research proposing exactly that kind of unified language. It's called Tensor Logic, or TL. Pedro Domingos is behind it. And our mission today, really, is to unpack this. How can this one core idea, the tensor equation, potentially become the lingua franca for all of AI, bringing deep learning and symbolic logic under one roof?
Right. And to get there, we need to start with the absolute core insight. And it's beautiful, really, because it's so simple at heart.
Okay.
The insight is that logical rules, specifically things like Daylog rules and tensor summation, they're basically the same mathematical operation.
Wait, hang on. A logic rule, like if X is the parent of Y and Y is the parent of Z, then X is the ancestor of Z. That feels totally different from like multiplying matrices together.
It feels different, but mathematically, the structure lines up perfectly once you represent the logic correctly.
How do you represent it?
Think about a simple relation like neighbor ij in a social network graph. It's either true or false for any pair ij.
Okay, binary.
That relation. It's just a compact way of writing down a sparse Boolean tensor.
A tensor, like a multidimensional array.
Exactly. For neighbor, ij, it's just a matrix, a 2D tensor. You put a 1 where the relation is true, they are neighbors, and a 0 where it's false. Most entries will be 0, hence sparse.
Okay. So the facts, the relationships, become this grid of ones and zeros. The symbolic base becomes an algebraic object.
Precisely. You translated the what is true into a tensor.
Yeah.
Now, what about the rule? The how to infer new truths.
Yeah, the AX-Z example you mentioned earlier. Aunt X-Z, sister XY, parent YZ. How does that become math?
Well, what is that rule actually telling us to do? It says find some individual Y who is both the target Z's parent and person X's sister. You're looking for a connection.
A join, essentially. Find the common Y.
Exactly. A join operation followed by projecting the result onto X and Z.
Yeah.
Now, how do we do that join algebraically?
Matrix multiplication.
Almost. Specifically, Einstein summation, or Eintinsum. It's just a super concise way to write operations like matrix multiplication, dot products, transposition, sums, all sorts of tensor operations.
Right, Einsum. I've seen that in code. It's powerful, but a bit cryptic sometimes.
It is. But here's the key. When you multiply the sister tensor, let's call it Einc by the parent tensor, pi I, using Einsum, the repeated index, high, signals the Einsum operation to sum over all possible values of y. That is the join. It's searching for all the connecting paths through any y.
Oh, I see. If there's any y where sister xy is 1 and parent yz is 1, their product is 1. When you sum across all y, if you find at least one such path, the sum will be greater than 0.
You got it. So if we write the relations as Boolean tensors a key, the rule literally becomes a tensor equation, I8.
And the Heaviside step function, it just snaps the result back to Boolean. The summation might give you, say, 2 if there are 2 intermediate siblings y.
But geotech XX just checks, is the result greater than 0? If yes, output 1, true. If no, output 0, false. Crisp logic again.
Wow, okay. So the core of tensor logic is just this. A tensor equation where the left-hand side is derived from some tensor operation, usually an Einstein-like join on the right-hand side, possibly with a simple function like hx applied.
That's the fundamental building block, the sole construct, as the paper puts it. Everything else is built from that. LHS equals some combination, join projection nonlinearity, of tensors on the RHS.
That is incredibly elegant. It implies the same math, the same optimized libraries used for deep learning GPUs can now directly run formal logical deduction.
That's the unification right there.
Okay, so if tensor logic really is this unified language, the big question for me is, does it actually make the current mess of deep learning models simpler? Or is it just, putting new labels on the same old complicated stuff?
That's fair. I think the argument is that it does simplify things because you don't need radically different frameworks for different model types anymore, meaning an MLP, a simple feed-forward network. That's just a tensor equation, a recurrent neural network, an RNN, also just a tensor equation.
Okay, basic ones maybe.
Yeah.
But RNNs are powerful, right? Turing complete.
Exactly. And if an RNN is just a TL equation, that means TL itself is Turing complete. It can, in principle, compute anything any other computer can.
Fine, but what about the really specialized architectures, like convolutional neural networks? CNNs, they have those sliding filters, pooling layers. That feels very specific, very geometrical. How does a simple tensor equation handle that?
That's actually one of the really neat parts. It uses something called index functions right inside the tensor equation.
Index functions?
Yeah. Instead of needing a whole separate conv2d layer type in your software library.
Which has tons of hidden code.
Right. The TL equation itself defines the geometry. So for the output tensor, say output y, its value might be defined by summing over a patch of the input tensor, like input x plus dx, y plus day, where dx and d define the filter shape.
So the indexing math is the convolution.
Precisely. And pooling, same idea. The output index might be defined using integer division, like pooled xs, ys, where s is the stride. The equation tells the system, grab this block of inputs, aggregate them, and put the result at this calculated coordinate. The spatial logic is in the tensor indices themselves.
Huh. Okay, that is clever. No need for specialized code, just clever indexing. What about graphs? Graph neural networks, GNNs, are everywhere now. They work by passing messages between neighbors.
GNNs are almost trivially easy in TL. Remember our neighbor, XY, Boolean tensor.
Yeah, the sparse matrix of connection.
That is the graph structure. When a GNN aggregates features from neighbors, say putting the result in tensor Z, based on input features F.
How does it do that?
It's literally just a tensor joint, ZX nexi phi, summing over Y.
Wait, the neck tensor has zeros for non-neighbors.
Exactly. So that multiplication automatically zeroes out the features F of any node Y that isn't a neighbor of X. You're naturally left summing up only the features of the actual neighbors.
Okay, that sounds almost too simple compared to setting up GNN layers in PyTorch or something. Are we sure we're not losing something? Expressiveness. Performance.
That's the crucial point. You're not losing expressiveness. The tensor equation is the GNN aggregation. And performance, because this all compiles down to highly optimized GPU operations like Einstein.
The same ones deep learning already uses.
You get that massive parallelism. What you gain is clarity. The GNN's logic is right there in the equation, not hidden inside library calls.
Okay. I'm starting to see the pattern. What about the elephant in the room? Transformers. LLMs. The foundation of everything right now.
Transformers are fundamentally built on matrix operations, so they fit beautifully. The query, key, and value matrices, they're just the result of multiplying the input embedding tensor, 6B or Diller, by some weight matrices. Simple tensor equations.
Somewhere times t cruise, 6 times 2 $. Yeah, okay.
Then the core attention mechanism calculating similarity by multiplying Q and K transpose, scaling, softmax, then multiplying by V.
All matrix sensor operation.
Every step. The paper actually shows the entire multi-headed attention mechanism, including layer normalization, the residual connections, everything can be expressed in maybe a dozen or so TL equations.
Just 12 equations for self-attention.
Something like that, yeah.
Yeah.
It's incredibly compact.
So whether it's vision with CNNs, graphs with GNNs, or language with transformers, under TL, It's all just variations on this one core theme,
Yeah.
the tensor equation.
And you could still do the classic symbolic deduction we started with, too.
It really does seem to cover the whole spectrum then.
And this unification, this common language, it paves the way for what I think is the real breakthrough here, the most innovative part of tensor logic.
Which is?
Performing sound, reliable reasoning, using the learned, fuzzy embeddings that deep learning is so good at creating. This is the bridge between generalization and rock-solid reliability.
Okay, that's huge. Because right now, that's the big problem with LLMs, isn't it? Amazing generalization, fluent text, but they hallucinate. They make stuff up. Their knowledge is fuzzy, opaque.
Exactly. There are no guardrails of logic. TL tackles this head-on. It allows an entire relation, like our ant tip z, to be represented not just by zeros and ones, but by a tensor containing continuous values and embedding. Let's call it embantlaris.
So a fuzzy representation of antness?
Sort of, a distributed representation learned from data. Now, reasoning like forward or backward chaining can happen directly over these embedded rules.
How does that work without just evolving into fuzziness again?
This is where the learned embeddings do something amazing. They naturally enable analogical reasoning.
Analogy? How?
Well, when you learn embeddings for all the entities, people, concepts, whatever, you can calculate a similarity matrix. Just multiply the big embedding matrix by its transpose. Let's call it Symx, X.
Okay, so this matrix tells you how similar entity X is to entity X based on everything the model learned.
Exactly. Now, during reasoning, similar objects can effectively borrow inferences from each other, weighted by their similarity.
Can you give an example?
Sure. Let's say the system is reasoning about, I don't know, a specific type of bird, maybe a peregrine falcon. The embeddings know it's very similar to other birds of prey, like a kestrel. If there's a rule that applies strongly to kestrels, maybe about hunting behavior, the peregrine falcon can borrow some strength for that inference because Simprac kestrel is high.
Ah, okay. It's like using precedent in law, but the precedent is learned similarity, and the weight is how similar they are.
That's a great analogy. It combines the power of similarity generalization with the structured logic of the rule's compositionality.
Okay, that sounds powerful for creative tasks or dealing with incomplete knowledge, but it also sounds like exactly where hallucinations come from. How do you make this reliable when you absolutely need precision, like for math problems or generating code or scientific modeling?
This is the cleverest part, I think. The control mechanism. The temperature parameter, T.
Temperature, like in statistical physics.
Kind of, yeah. It's a hyperparameter, a setting you choose, that gets applied within the math of each tensor equation, typically scaling the input to the sigmoid or step function. Think of it as a dial.
A dial for what?
A dial controlling the style of reasoning.
How so? What happens if I turn the dial down?
If you set T to zero temperature, the reasoning becomes purely deductive, strict logic.
How does TO0 do that?
Mathematically, setting T to 0 makes the sigmoid function behave exactly like the heaviside step function we talked about earlier. It forces outputs to be hard zeros or 1 and ills. And crucially, it effectively makes that similarity matrix, Symx, Xir, behave like the identity matrix.
Meaning?
Meaning an object is only similar to itself. No borrowing of inferences. An inference only fires if the logical conditions are met exactly. When T0, the system operates under strict Boolean logic. The sources argue this makes it essentially immune to hallucinations.
Immune. That's a strong claim.
Because it's not guessing based on fuzzy similarity anymore. It's performing verifiable deduction based on the rules and facts provided, just like Prolog, but potentially overlearned embedded representations.
So, high-stakes task, like verifying some critical piece of code, set T0, get verifiable, logical deduction.
Yeah, exactly.
More exploratory task, like brainstorming story ideas. Turn T up, allow that analogical reasoning, let it borrow related concepts.
Precisely. You get this spectrum from pure logic to analogy, controlled by one parameter. And this control is key for transparency and reliability, the very things missing in many current systems.
And because it's all tensor equations, you can presumably inspect the intermediate tensors at any step, see how it reached a conclusion.
That's the idea. Explicit equations mean traceable reasoning, no more opaque blob of weights.
Okay, it's a pretty compelling vision. A single language, tensor logic, handling the symbolic stuff, the deep learning stuff, and everything in between, offering both that powerful generalization and tunable reliability via the temperature T.
It addresses the core weaknesses of both classical AI and modern deep learning, potentially.
The challenge, though, is always adoption, isn't it? How does something like this move from a cool research paper to actually being used?
Yeah, that's the practical hurdle. It needs momentum. The paper suggests, quite pragmatically, that TL needs to kind of ride the waves of the current AI boom.
And critically, it mentions backward compatibility with Python. That seems essential.
Absolutely key. You can't just tell everyone to ditch their entire stack. The idea seems to be that TL could start as maybe a more powerful extension of Python's existing Einstein.
So you could gradually introduce TL equations for reasoning tasks into your existing NumPy or PyTorch code.
Something like that.
Yeah.
Make it an evolution, not a revolution for developers. Ease the transition.
But what's the killer app? What makes people want to switch?
I think it boils down to fixing those two big pain points we keep mentioning. The opacity and the unreliability, especially of LLMs.
Right, hallucinations and black boxes.
If TL can genuinely offer a way to build models for reasoning, math, coding, tasks that demand precision, and guarantee you can switch into that verifiable T0 deductive mode, that's huge.
That would be the selling point. Moving away from just hoping the model is right towards having verifiable equation-based logic you can actually check, like debugging code instead of just prompting a black box again.
It's a potential paradigm shift for trust in AI systems. From trust me, the weights are good to here are the equations, verify them.
A future where generalization and reliability aren't an either trade-off, but just different settings on the same dial.
That's the promise, yeah.
Okay, so let's wrap up with a final thought for you, the listener, to chew on. We talked about using that temperature T to control the style of reasoning deductive versus analogical.
Dialing between logic and similarity.
But the source material hints at something even wilder. Think about complex programs today, scientific simulations, business logic. They often have lots of rigid, if-then-else statements controlling which equations get run when.
Yeah, the control flow logic that wraps the core calculations.
TL suggests, what if those Boolean control statements themselves were represented as tensors? And what if, instead of being strictly Boolean, 0 or 1, they were relaxed to be numeric continuous tensors?
So the control logic could also become fuzzy learnable.
Exactly. The implication is that the entire control structure of a program could potentially become automatically learnable and adaptable based on data. So here's the question to ponder. What kind of program, maybe a scientific model or business process you use, has rigid rules today that you wish could learn to adapt its own rules, its own decision logic, based on the outcomes it sees? What could that enable?